We have just finished examining the world of kinematics, the study of moving objects, ignoring the forces affecting them. But now, let us look at those dear forces and their role in the motion of objects. Let us remember that football from way earlier. A force can be thought of as any interaction that, if unopposed, will alter the motion of an object. The standard international unit for forces is the Newton. An object that is moving may accelerate if a force is acting upon it. Take a football, for example. If it's standing still, I can kick it so that it speeds up. I have applied a force on it. If it's moving, I can slow it down by applying a force, or I can change its direction by applying a force. In all these applications of forces, I have caused the ball to accelerate. Yes, even if it's just changed direction, it's accelerated. Even though it did not change speed. Remember, acceleration is defined as a change in velocity, not speed. And since velocity is a vector, a change in the direction of movement changes the direction of the velocity vector. And so that change in the velocity was acceleration. We will return to this concept of forces causing acceleration very soon. Multiple forces acting on an object can cancel each other out. If you are grabbing the football, you are pulling it, and a force of X newtons is being exerted on it. The force vector is pointing toward you. But if at the same time your friend tries to grab the ball from you because they want to play with it, they are also exerting a force on it. The force vector is pointing in their direction as they are pulling it toward them. If the magnitude of the two forces is equal, if both are X, then they will cancel each other out, and the overall force acting on the ball will be zero, and it will not be going anywhere. None of you will be able to enjoy football. Meet Sir Isaac Newton, just about the biggest genius ever. He was born in the 1600s in the United Kingdom as the son of a poor farmer. He would go on to revolutionize science and become one of humanity's most compelling characters. Among his vast array of achievements is his book, Mathematical Principles of Natural Philosophy. Natural philosophy was basically the physics of his time. In it, he propounded his now famous 3 laws of motion. Those 3 laws today remain an important part of physics, helping explain how motion works. Now, we've spent a lot of time here on Earth, and although it's been fun, to really demonstrate these laws, we need to get out of here. Right, we're no longer earthbound. Let's get to work. Remember how we talked about an unopposed force causing acceleration? Well, that's exactly what Newton's laws are about. The first of Newton's 3 laws is often called the Law of Inertia, and it basically states that an object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity unless acted upon by a net external force. This basically means that if a force is being exerted on a body, the body will accelerate. And if there is no force, it will not accelerate. Its velocity will not change. This law at first may seem to be incompatible with our normal experiences. It seems to suggest that if I kick a football, it should keep moving. When I kicked the ball forward, for a short moment in time, I exerted a force on it and caused it to move away from me. In that short moment in which my foot was in contact with the ball's velocity was increasing. It was accelerating because in that space of time I was applying a force on it. And after that, the ball left my foot. Assuming that the kick lasted for half a second and the acceleration I gave the ball was positive 30 meters per second squared, the velocity with which the ball left my foot can be found using this kinematic equation. Once the kick was over, the ball had no more force acting on it, and so therefore had no more acceleration. Thus, it should now continue to travel in the direction of my kick at a constant speed of 15 meters per second for eternity. This is, of course, unless an opposing force acts on it. Similar is the case for the book. But that's not what we see. they do not travel like that for eternity. They come to a stop within moments. Why? It's not like there's some magical opposing force to slow down and decelerate the objects as soon as they begin moving. Or is there? There are many different types of forces that we know of in the universe, several of which will be looked at later. One of these forces is called friction, and it is the reason why these objects were decelerating. What is friction, you ask? Well, whenever an object moves along a surface, such as the ball moving along the surface of the earth, in our example, the surface exerts a force on the object. One component of the force exerted is the frictional force, or the force of friction. This force is parallel to the surface and opposite to the direction of the moving body. Since it acts opposite the velocity, it causes deceleration. There are two different types of friction: static friction and kinetic friction. Static friction is a friction that resists the initiation of motion. It tries to prevent two surfaces from sliding across each other. Static friction is the reason why I am unable to push this couch along the floor. However, if I could push it hard enough, eventually I could overcome the opposing force of static friction, as it has an upper limit. Say I do manage to overcome the static friction and get the couch moving because I'm a strong boy. Then the moving object will be at war with kinetic friction, which is the frictional force that tries to decelerate moving objects, as it acts in the opposite direction of motion. However, even kinetic friction will fail to have any considerable effect on the movement of the couch. This is because I am, as was already established, a strong boy. Friction can cause heat and sound. Try rubbing your hands together to observe that. No matter the surface along which your ball is rolling, there will always be some friction. However, the strength of the frictional force can vary depending on the material. Rough and bumpy materials tend to be more unforgiving when it comes to friction than as compared to smooth materials. If I kick a ball on a rough patch of grass, it will decelerate much quicker than if I kick it on flat tarmac. Here in outer space, since I have no surface along which I'm kicking the ball, there can be no friction. So here the ball will continue to travel forever and ever. We have observed the link between roughness and friction. However, we are not 100% sure as to what causes friction, and research regarding this topic continues to go on today. Anyway, let's get back to Newtonian motion. In his first law, Newton is telling us that an unbalanced force acting on an object will cause acceleration. There could be 1, 2, 3, 4, an infinite number of forces acting on an object. But as long as the net external force on an object is 0, velocity will remain unchanging. If there is an external force acting on the object, it will accelerate. In his second law of motion, Newton takes this idea and runs with it. In it, he tells us that the force acting on an object is equal to the mass of the object multiplied by the acceleration that is caused by the application of the force. Or simply, F equals ma. Force equals mass times acceleration. Remember the football from earlier? I had accelerated it by 30 meters per second squared for half a second by kicking it, and therefore the velocity with which it left my foot was equal to 15 meters per second. The kick lasted half a second. That is how I know I had accelerated the ball for half a second. But how did I know that I had accelerated the ball by 30 meters per second squared? Well, I knew the mass of the ball was 0.5 kilograms and the force applied with my kick was 15 newtons. Therefore, I had merely to plug in the values into the equation. Boom! Say you're once again riding on the highway on an empty Sunday. You are moving at a constant velocity of 60 meters per second. Since velocity is constant, there is no net force acting upon your car. But then you spot a pizza shop ahead in the distance and you become hungry. You want to have pizza, so you slam on the accelerator, and within a space of 5 seconds, your speed increases from 60 to 100 meters per second. We can calculate the acceleration of your car using this kinematic equation. Your final velocity after you slammed the accelerator was 100 meters per second, and the initial velocity of the car before the thought of pizza landed in your mind was 60 meters per second. The time for which you slammed the accelerator was 5 seconds. Let's plug the values into the equation. Acceleration was 8 meters per second squared. Since the acceleration caused your velocity to increase, we can say that it was in the same direction as your velocity. Furthermore, there also had to be a force present for the acceleration to occur in the first place. That force was induced because you pressed the accelerator to accelerate. Let's calculate the force caused by the accelerator. The mass of the car, let's suppose, is 1000 kilograms, and the acceleration we know was 8 meters per second squared. Therefore, we can compute that the force was 8000 newtons. By the way, what exactly is mass? I mentioned earlier that it's often defined as the amount of stuff something is made of, but it is also thought of as a measure of an object's inertia. Inertia is the tendency of an object to keep doing what it's doing. If there are two motionless objects in front of you and one has a mass of 5 kilograms while the other 10 kilograms, the 10 kilogram object will be harder to get moving than the 5 kilogram object. Similarly, the 10 kilogram object will be harder to stop once in motion, that is compared to the 5 kilogram object. From this, we say that the 10 kilogram object, since it has a higher mass, will have a greater inertia. F equals ma may not seem too impressive to you, but get this, it is awesome. Used everywhere by physicists, scientists, and engineers, without F is equal to ma, the world would suck a lot more than it already does. Every action has an equal and opposite reaction. That's it. That's the law. It's not the lyric of a nursery rhyme. It's the law. This law is often quoted outside the context of physics, and wrongly so. This law is often called action-reaction, and it tells us that forces exist in pairs. If I punch my punching bag, my fist is exerting a force on the punching bag. This law tells us that in return, the punching bag will exert a force back on my fist that is equal in magnitude and opposite in direction. That's right. Every time you punch something, it punches you back. This law is beloved by both physicists and lay people alike. However, it is unfortunately often misunderstood. Wait. If this law is true, how could anything even move? See, if I push this book along a table with a force of 1 Newton, this book will impart an opposing force of 1 Newton in return. This raises the idea that it's impossible for the book to move in the first place, since the force I'm applying and the force the book is applying will cancel one another. This is an understandable misunderstanding. Let's clear it up. The idea that the book shouldn't move only arises when we treat my hand and the book as one system. But really, when it comes to motion, we do not treat them as one system. We treat them as two individual systems. My hand is separate from the book. When we look at my hand, we only analyze the forces acting upon it, not the forces that it exerts on the objects around it. Similarly, when we look at the book, we only consider the forces that affect the book, and not the forces that the book exerts on things around it. If this view is opted, and we consider the sliding book as the system of interest, we can see that a force is acted upon it, and the force that it exerts in return does not affect its motion. It moves. So, those were Sir Isaac Newton's 3 instrumental laws of motion. They forever changed humanity, and you really have to wonder how big Newton's brain was. How on earth did he conjure up these laws? Well, Newton was a force of nature, no doubt, but he stood upon the shoulders of this guy, Galileo Galilei. Hi, thank you for watching this video. If you feel certain explanations weren't understandable, or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.